So our purpose of doing the discrete time Fourier transform was really to understand how can we look at signals in a different way and get some insight about signals. And we looked at how does the Fourier transform tell us about the frequencies that are present in a discrete time signal. Now our goal is to understand how does the Fourier transform help us understand the actions of discrete time systems. So we did a similar exercise for continuous time systems using continuous time Fourier transform. Now our goal is do a similar kind of activity for discrete time Fourier transform, discrete time systems. And for that, the first thing we'll do is look at the convolution property of the discrete time Fourier transform. The convolution property says that if you have two sequences whose Fourier transform is given by G and H, and you convolve them in time, so you calculate Gn convolution with Hn, then the resulting output has a Fourier transform which is given by the multiplication of the individual Fourier transform. So it's exactly the same property as the continuous time world. There is no difference in this setting. Convolution in time means you multiply your Fourier transform in frequencies. Okay? We won't go into the proof of that, but let's understand what is the implication of this property in terms of our understanding of discrete time systems. So this property helps us understand the effects of discrete time systems on signals in terms of frequencies. So we know what a discrete time system does in terms of time domain. If you input a signal Hn, and the discrete time system, I should say discrete time LTI system, this only works for LTI systems. So we know that an LTI system can be fully described by just the impulse response, which is the response of the system when you input an impulse into the system. So if the LTI system has impulse response Hn, then the output Yn of the system is simply convolution of input and the impulse response. Now if I use the convolution property, if I look at in the time domain, it's very difficult for me to comprehend that the output is input convolved with the impulse response. But what is really the system doing? To do that, we can look at the system's output in the frequency domain. So we can say, let's compute the Fourier transform of Yn. Well, that's the Fourier transform of Xn convolution with Hn. So let's call the Fourier transform of Yn y of e to the j omega. Now using the convolution property, we know that that is simply equal to x of e to the j omega, h of e to the j omega. And this can be used to understand the effects of a discrete time system, discrete time LTI system on the input frequencies. Since we went over that in rather significant detail for continuous time systems, I'll not spend too much time, but I'll try to give you the gist of it. The first part is that if your input signal has no frequency at a particular discrete time frequency little omega, So if x of e to the j omega equal to 0 for some omega. So let's say that x of e to the j omega equal to 0 for omega equal to pi by 4. Then what will be the output frequency at pi by 4? What will be the strength of the output frequency at omega equal to pi by 4? So y of e to the j omega in that case will be equal to 0. Doesn't matter what your impulse response was. So what it means is that discrete time LTI systems, if your input signal does not have a frequency, a discrete time LTI system cannot insert that frequency in your output signal. If I am a singer and I don't have a frequency at, I absolutely produce no frequencies at, let's say, 10 kilohertz or 11 kilohertz, no matter what kind of processing I do, I cannot insert that 10 or 11 kilohertz frequency after the processed song. Okay. So discrete time LTI systems cannot add new frequencies that are not present in input signals. Now, the second property is that if the system, so let's say the system is such that h of e to the j omega equal to 0 for some omega. Again, when I'm writing it like this, I'm using a particular value of little omega, okay? So little omega could be any number between minus pi and pi. Now, if your impulse response's Fourier transform is such that it hits 0 at a certain location for some value of little omega, doesn't matter how strong your input signal was at that frequency, your output frequency will be again 0. So what that means is that discrete time LTI systems can be used to kill frequencies in the input signal. Again, let's take the example of a song that you are recording, and in the background there is a continuous, let's say, a screeching noise of some frequency. Right now we'll just talk about discrete time world. So there is a screeching noise of frequency pi by 3. You can try to design a system whose impulse response's Fourier transform is 0 at that frequency. And when you process that song, at the output, you will get rid of that screeching sound. So that is one thing that LTI systems can do. And in the lingo, which we'll talk about later, that's called a notch filter. Right? You can pick out certain frequencies and kill them. Okay. The third is that so let's now assume we have already covered the case that either the input signal has no frequency or the impulse response's frequency is 0 at a certain point. Now let's take the case that both x of e to the j omega and h of e to the j omega are not equal to 0 for some omega. So let's say omega is pi by 2, neither x e to the j omega is 0 nor h e to the j omega is 0. What happens to the output? Now in that case, you are multiplying two complex numbers. Right? This is a complex number, so let's write this complex number in polar form. Absolute value of, so this complex number has an absolute value and it has a phase. Similarly, h has an absolute value and a phase. So the question is, what happens to the absolute value of the output frequency? So y of e to the j omega, I can also write it in terms of absolute value times its phase. And using just the property of multiplication of complex numbers, we can see that in that case, the magnitude of the frequency at little omega will be equal to the magnitude of frequency that x has at little omega times whatever is the strength of the Fourier transform of your impulse response at that frequency. So this means that discrete time LTI systems can either scale up or scale down frequencies of input signals. So it's the same equalization kind of principle that we saw for continuous time signals. Let's say you have an input signal where the frequency pi by 2 has certain strength, right? That corresponds to, let's say, the bass in a song. And you want to double the contribution of that frequency. In that case, you will design a system such that the Fourier transform, so this thing, in that case, is equal to 2 at that frequency. And then you will double the contribution of that frequency in your output signal. On the other hand, let's say you don't like that frequency that much in your song, and you want to reduce it by half, then you will actually design a system such that h of e to the j omega absolute value is 1/2 in that case. And your output will be one half of your original input strengths. Okay? So this is what happens to the magnitude of your input frequencies. They get scaled up or down as a function of the strength of the Fourier transform of your impulse response. Now, the phases, of course, gets added up. So the output phase of a frequency is going to be the phase of the frequency in the input signal plus the phase of the frequency in the Fourier transform of your impulse response. So to recap, discrete time LTI systems effectively, the only thing they are doing they are changing the strengths of your frequencies and they are changing their phases. They can either scale up frequencies, scale down frequencies. They cannot add new frequencies into the system. They cannot shift the frequencies. Okay, so let's look at an example, a very simple example of an LTI system and use this property to interpret what is that LTI system doing. So suppose you have an LTI system which has an impulse response Hn equals to delta of n minus 10. Okay. Now, what is this LTI system doing to the input frequencies? So one is you could just compute the convolution. You can compute the convolution yn equal to xn convolved with hn. And I'll leave that as an exercise. It's a really simple exercise that the answer will be xn minus 10. So the output is delayed version of the input, delayed by 10 samples. But what is this doing in the frequency domain? The LTI system, what is this doing in the frequency domain? So in the frequency domain, y of e to the j omega is x of e to the j omega times h of e to the j omega. Now, what is h of e to the j omega? We know that delta n Fourier transform is 1. We also know that shifting a time domain sequence gives rise to a phase shift. Right? So using these two properties, we can write down the Fourier transform of the impulse response. It's e to the j omega 10 using the time delay property of the Fourier transform, right? So the property we had covered was that if you shift a sequence by a certain amount, it causes a phase shift to the Fourier transform. And since my Fourier transform is 1, I only multiply it by 1, so it's e to the minus j omega 10. So if I write that down, it means that y of e to the j omega equals to x of e to the j omega times e to the minus j omega 10. This means that my magnitude of my output signal frequencies is simply the magnitude of my input signal frequencies, because the magnitude of h is simply 1. And the phase of my output signal frequencies is phase of my input signal frequencies minus omega times 10. So what this says is that an impulse response delta n minus 10. Now you can look at it in the, you could have solved it directly using the properties of the Fourier transform on the output expression like this xn minus 10. But so we know that the output is simply a delayed version of the input. And when we look at it in the frequency domain, we see that the magnitude is not affected. The only thing that is affected is that there is a linear phase. So this is a linear phase shift with a slope of minus 10. So all that has happened due to an impulse response delta of n minus 10 is your output frequencies you still have the same output frequencies, same strength, but their phase has been shifted by minus 10 omega. So every omega frequency has its phase shifted by minus 10 omega. Okay. So what we say is that linear phase shift simply means the system is delaying the input by a certain amount of samples. And nothing further. Now, this is a very simple example that I just gave to convey that you can just use that convolution property that we talked about to compute what's happening to the output frequencies. Let's look at now a little bit more complicated example of what is called an inverse system. Suppose you have an input signal xn, and the input signal passes through an LTI system hn, and you get yn. Okay. So the example I will give you is you have your cell phone, you're speaking on your cell phone, the cell phone transmits some signal, and I won't go into the details, it's not a practical realization, but we'll assume that it happens, right? That your cell phone your cell phone signal is now passing through this environment to reach the cell tower. Assume the movement of your RF waves from your cell phone to the cell tower can be modeled as an LTI system. Okay? Now, what happens is because of the movement of things and reflections, you create some distortion into the input signal. So what your cell phone transmitted, the cell tower does not exactly receive that signal. And so this is sort of like modeling of an environment. And what you want at the cell tower so that you can transmit to the other recipient and they can hear you clearly, what you want is you want to invert the effects of this environment. So what you do is so this is a system which is given by nature. You cannot get rid of this system. So this is given by nature. So now you design another system, Gn, to invert the effects of nature. Okay? So this is inverse system. And what's the goal of the inverse system? That you get back the signal that your cell phone transmitted. So what is the desired output here is you want the desired output to be x of n. You want the cell tower to reconstruct what was transmitted. So your goal now is to design this system. Now you can write down the convolution expression you want. So of course the desired output let's call that desired output x tilde of n, and we'll try to make it to xn. Okay. So what's the input-output relationship? Let's do it block by block. So yn in time domain, first of all, yn is xn convolved with hn. And then if I look at the second block, I have x tilde of n, which is the output, that is equal to the input, which is yn, convolved with gn. Okay. So if I combine the two, I get x tilde of n equal to xn convolved with yn convolved with gn, convolved with hn, and then convolved with gn. So the goal then is design gn such that xn convolved with hn, which you assume convolved with gn, equals to xn. Right? Now this is a difficult problem to wrap your head around if you just look at the convolution expression. You can keep on staring at it. It may reveal you the answer or not. But the way we can do that is using the frequency domain expression. So this is the frequency domain equivalent of these equations. So what is that? That y of e to the j omega equals x of e to the j omega times h of e to the j omega. Similarly, x tilde of e to the j omega equals y of e to the j omega times g of e to the j omega. And so this means that if I input the value of y e to the j omega, I get x tilde e to the j omega is x of e to the j omega times h of e to the j omega times g of e to the j omega. So now what I want is in frequency domain, the goal is x tilde of e to the j omega equals x of e to the j omega. Because if the Fourier transform is the same, then the time domain signal is the same. So if I do that, then what I'm saying is that x e to the j omega, h e to the j omega, g e to the j omega is equal to x e to the j omega, which means I want this product to be equal to 1. And so then the goal becomes that h of e to the j omega, g of e to the j omega equals to 1. And since it's multiplication, if h of e to the j omega is not equal to 0 for all little omega, right? If it is not equal to 0, then you can simply do multiply and divide by h. So this means that your g should be equal to 1 over h e to the j omega. Now, what this means is that you should build a system. So once you have this, you can compute its inverse Fourier transform to compute Gn. Right? And you can use a MATLAB to do that, for example, for you. And that's how you can design an inverse system. Right? Now, let's think about it. What is though this? So this is your design system in frequency domain. And Gn will simply be equal to inverse Fourier transform of this thing, which may or may not have a closed form expression. Okay, keep that in mind. Now let's look at what does an inverse system do in terms of frequencies. What is the meaning of this? That g of e to the j omega equal to 1 over h e to the j omega. Okay. Well, to do that, let's write it in polar form. Let's write h of e to the j omega equal to its magnitude times its phase, e to the j, h, e to the j omega. So if I write it that way, then I get this times e to the j, h, e to the j omega. Right? So this is the absolute value is a real number. I can just keep it there, and this complex phase, I can just take it upside. So I'll get e to the minus j, h of e to the j omega divided by h e to the j omega. So if I now relate the two for the inverse system, I can always also write g of e to the j omega. In the polar form, it's g of e to the j omega, e to the j phase of e to the j omega. If I compare the two equations, what do I see? The magnitude of my inverse system is simply the inverse of the magnitude of my nature system. So what it is saying is that an inverse system should be built if nature scales up frequencies by a factor of 2, my system should scale down that frequency by a factor of 2. If nature scales down something by a factor of, let's say, 3, my system should scale up that frequency by a factor of 3. It's 1 over the whatever the scaling nature is doing. And of course, now it becomes clear the condition on your nature cannot kill a frequency. Nature must not kill a frequency. Why? Because if nature kills the frequency, then I cannot invert it. I cannot do 1 over, once a frequency goes 0, I cannot bring it back. But if nature doesn't invert a frequency, it doesn't kill a frequency, then I can always scale it back to where it was. Of course, I'm right now ignoring the noise effects. These things become more complicated when you have noise. And what is the phase? The phase of my inverse system is simply negative of the phase of my input signal. Okay? So if nature shifts my frequencies this way, you want a system that will shift your frequencies this way. So just a complete reverse of whatever nature is doing. Right? And this inverse system basically comes up again and again in many applications. Applications of this involve communications, wireless communications, wireline communications, and so forth. Okay. Not surprisingly, this effect is also called, in communication language, it's called equalizer. It's equalization. You are equalizing the effects of what the nature is doing. It comes up in echo cancellation. It comes up in blur cancellation in images. Your cameras, you shake your hand, it causes some blur. It tries to remove that blur, the picture that you see. Noise cancelling headphones, that's another example of an inverse system. Okay? Now, they are all not based upon LTI systems, but the basic principle is the same. What is noise cancelling headphone? There is something happening outside. That's nature. And inside your headphone, they are trying to do processing that inverts that effect outside. Now, it is not perfect if you have ever owned a noise cancelling headphone, but it tries to do a good enough job. Okay. Okay, so let's then talk about some of the terminology that comes up when we talk about LTI systems. Since we now know what is the effect of LTI systems in terms of frequency. So let's say an LTI system has an impulse response and it has a Fourier transform h of e to the j omega. We already know we call this impulse response. Now, the Fourier transform of the impulse response, we give it the special name frequency response. The reason is because it tells us how the LTI system is going to affect the input frequencies. So what will happen to the if there is an input frequency, what will be the response to that input frequency? So it's called frequency response. And of course, your frequency response will be almost always complex valued. So you can write that in terms of its magnitude and its phase. And not surprisingly, this part, the magnitude of your frequency response, is called the magnitude or response, which means it tells you how does your system scale up or down the contribution of individual frequencies. The frequencies could be shifted in time, but they will have the same strength. Okay? And this part, which is the phase, is called the phase response. So it's effectively like the Bode plots that you guys should have done in Principles of EE2. And since the magnitude response is really telling you how things get scaled up or down, it is common to describe the magnitude response in dB scale. So you often look at 20 log to the base 10 of h of e to the j omega. Okay. Which, if it's positive, this means that it's gain in dB. And if it's negative, then you say it's the loss in dB. Because all it is saying is your input signal will have certain frequencies. There is no absolute number to the frequencies that you will input to the system. So what we are really concerned about is if you input a frequency at this level or at this level, what's the scaling of that? If it's 2 times, 4 times, 8 times. So that's why we like the dB scale. You know, we say, oh, it's going to give a gain of 3 dB. So it's going to increase that frequency by a factor of 2, whatever was the input frequency strength. Right? Or it's going to decrease the input by a factor of 2, so it's going to create a loss of 3 dB. So you don't talk about absolute values, so that's why you often see these plots in the dB scale. Okay. And of course, if you are ever hitting 0 in your frequency response, then you will see a big dip in your dB plot. So similar to the case of continuous time systems, then of course you could be given a requirement that design an LTI system which has a particular frequency response, and then you will design that. But there are some standard filters which appear again and again, just like in continuous time systems. So first of all, when you're talking about discrete time systems, we tend to call them filters because it's like filtering the frequencies. And common types of discrete time filters, they are very similar to the continuous time filters, with the caveat that discrete time frequency response, discrete time Fourier transform is periodic. So you have to always keep that in mind. So you could be given we'll be talking about only frequency response. The idea is that you have h of e to the j omega. And in particular, I'll talk about just the magnitude response. Phase is a little complicated. Sometimes you cannot control the phase always. Okay? But even if you cannot control the phase, if the magnitude has a certain shape, we still give it the same name. So the first type of filter, it's called low pass filter. Now, what is a low-pass filter? Just like the continuous time world, a low-pass filter is a filter that passes all the low discrete frequencies. So in the discrete world, we know that, first of all, you will have periodicity after minus pi and pi. And low pass means that you are around zero frequency, 0 radians per sample. So a low pass filter will have, an ideal low pass filter will have a shape like this. This will be some number little omega c. This will be some number minus omega c. For example, this could be, let's say, an example will be pi by 4 or pi by 2. Right? So you will say, this is a low pass filter with a cutoff frequency of pi by 4. Saying that is enough to give you a sense of what it's doing. What is the filter doing? It's killing all frequencies between pi by 4 and pi. Now, there is periodicity, so you can't say it's killing all frequencies except up to pi by 4, because this filter, it's discrete time, so it is going to repeat itself, and this repetition will continue. Right? So in the main region from minus pi to pi, it has this shape, and then it repeats itself. Then we have the high pass filter. Now in the discrete world, we talked about the high frequencies are those that are around pi, minus pi, and then 2 pi shifted versions of those. So a high pass filter, in the continuous world, a high pass filter starts at a frequency and keeps on going. Okay, that's not what a discrete time high pass filter will look like. A high pass filter will have, it will have a cutoff frequency still omega c. Okay. But it will become zero after a while because of the periodicity. Because if it goes, it cannot go up to 2 pi. Because of the periodicity of discrete time frequencies. So the shape is a little different, but you say, well, this is a high pass filter. So again, let's say now, let's call it 3 pi by 4. Okay. So you say it's a high pass filter with a cutoff frequency of 3 pi by 4. Okay. Similarly, you have the equivalent version of band pass filter. So a high pass filter lets all the high frequencies but high discrete time frequencies pass and kills all the low discrete time frequencies. A band pass filter, just like the continuous world, lets all the frequencies in a band, the band could be anywhere between minus pi and pi, again because of the periodicity. So the band will have this shape, and then this thing will get repeated. So if you have minus 3 pi and 3 pi, and this is 2 pi, minus 2 pi, 2 pi, you will have these repetitions. So this could be omega c1, this could be omega c2. An example could be, this could be pi by 4, and this could be 3 pi by 4. Okay? But it's not going to hit pi. If it hit pi, then it will become a high pass filter. So this is a filter which is going to pass all frequencies between pi by 4 and 3 pi by 4 and kill all the rest of the frequencies between minus pi and pi. And after that, it will repeat itself. Okay. And similarly, we have the version of band stop filter. So a band stop filter will look like, it will pass all frequencies except some sort of except a band. So this is pi, minus pi, pi. So let's say it passes these frequencies, and then it passes these frequencies, and then it has to repeat itself again. So you say, so this is still called omega C1, omega C2, and you say it kills frequencies between omega C1 and omega C2, but only between minus pi and pi, and then you have to remember the periodicity of the discrete time Fourier transform. So if you compare it to the nodes on continuous time filters, you can see the similarities. The similarities are huge. The only difference is because of the periodicity. Once you go outside the minus pi to pi range, you have to be careful about that. There should be a component here. So let's consider now an example of a filter which is widely used in a number of areas. It's called the moving average filter. And the most common use of that, if you go to stock markets or you look at stock analysis, it's very commonly used in financial markets where people will be talking about 150-day moving average or 250-day moving average. Okay, so but when they talk about you have X days of moving average, what really they are saying is that you have an input Xn, which could be the price of a stock at different times of the day. Now a stock price, even if they plot it as a continuous time function, that's really a discrete valued signal because they are discretized even up to like milliseconds. They are not continuous valued. So you have a filter Hn and you get the output Yn, and the moving average filter is defined as this operation that the output is simply the summation of present and past m-1 inputs divided by m. Okay, so this is sum current and past m-1 samples and take the average. So this is called an moving average filter with parameter m. And what is the impulse response for this? So what is Hn? To calculate Hn, you simply input Xn equals to delta n, and that gives you Hn will be equal to 1 over m summation L from 0 to m-1 delta of n minus L, which means it's, so as you change different values of n, what you get is that 1 over m for all n between 0 and n-1 and 0 otherwise. So a moving average filter or a causal moving average filter basically starts at n equal to 0, go up to m-1, so a total of m coefficients, and the height of each one is 1 over m. That's the moving average filter. So you go to work in a financial firm and they say, let's apply 150 or 250 or 350 moving average filter, and you say, what should I select as my number of days? Well, to understand that, you have to understand what is the moving average filter doing to your input signal. So to understand what a filter is doing to your signal, one of the best ways of looking at that is in the frequency domain. So let's now understand what is the frequency action of this filter on the input signal. So how do we compute the frequency action? We find out, so what is the frequency response? Of a moving average filter. To do that, we compute its Fourier transform, discrete time Fourier transform, which is simply given by summation n from minus infinity to infinity xn e to the minus j omega n, or in this case hn. Now I input the values, so the filter is 0 for all values except from n 0 to m minus 1 e to the minus j omega n. Now this is the usual summation that appears again and again. So we can express it formally in the geometric sum notation. We have e to the minus j n, so our r is e to the minus j omega. Right? And since this is a finite sum, we don't have to impose the condition that our absolute value of r is less than 1, because there is no point that if you add a finite amount of numbers, they won't add up to infinity. Right? So a reminder, n equal to 0 to m minus 1, r to the n is equal to, so it's r to the 0, 1 minus r to the m over 1 minus r. Now r to the 0 in our case is 1. So what we get is 1 over m, 1 minus e to the minus j m little omega over 1 minus e to the minus j omega. Okay. Now you simply use the Euler's identity on the top and the bottom, and you simplify it, and what you get is 1 over m sine of omega m by 2 over sine of omega by 2 times e to the minus j m minus 1 over 2 omega. Okay. So you get this sine over sine expression. And this is the usual thing that you see in the continuous time, that actually this is like in continuous time, if you have a square function, the Fourier transform of that is a sinc. In the discrete time, this is effectively a square function. You have this boxcar function where hn looks like this. This is your hn. But you don't get the output is in sync because your discrete time Fourier transform is periodic. So this has, instead of sine over x form, this is sine over sine form, okay? Which ensures that it is like sync between minus pi and pi, but then it repeats itself. We'll take a look at it graphically also. Now we are really interested in understanding what does it do to the input frequency. So we look at the magnitude response. If you look at the magnitude response, then that is simply sine of omega m by 2 over sine of omega by 2, because the magnitude of this pure phase function is just 1. So let's try to understand what does this magnitude response look like.
Now on this screen you see two plots. One on the left hand side is the magnitude response of the moving average filter. The right hand side is the phase response. Let's look at the magnitude response. So the magnitude response is plotted for omega equal to 0 to omega equal to pi, because it's a real valued filter, so it's symmetric from minus pi to pi, and we can only focus on the positive frequencies. Now the red plot on this corresponds to m equals 5, and the blue plot corresponds to m equal to 14. And we see that as the length of the moving average filter, as the value of m gets larger, the moving average filter starts to look more and more like a low-pass filter. It dampens the higher frequencies. In particular, the bigger your m is, the more your moving average filter will dampen your higher frequencies and only let very low frequencies pass through. In particular, if your input signal was a pure cosine, let's say xn equals to cosine of 0.8 pi n.
Right. So xn equal to cosine 0.8 pi n, when we input that, our output will be, for m equal to 5, our output will be yn will be equal to 0, because this filter is going to make that entire input frequency 0. But even for the frequencies which are not at 0.8 pi, the filter is damping those frequencies. So the moving average filter, what it is really doing is it's damping the high frequencies, and high frequencies means fluctuations, right? The higher the frequency, the higher you have the rate of change of the signal. So if you then apply the same concept to, let's say this is an old plot of Apple. Now, of course, the price has gone way, way up. So this is the wiggly, really wiggly signal that you see in green, in bold green. That's the Apple stock price. And because we understand that stock prices really fluctuate a lot, what analysts want to see is a general trend of these stock prices. They don't want to see these large fluctuations because that doesn't give them an indication. So if you add a moving average filter, the higher the number of days that you are taking the average, the higher your high frequencies will be pushed down and your signal will become more smooth. Okay, it will start to change way, way less. So this plot is showing you a moving average of, there is a 10-day moving average, there is a 50-day moving average, and there is a 200-day moving average. And you see the 10-day moving average, so this is the 10-day moving average, is almost tracking the original stock price, but it has really gotten rid of some of those fluctuations because it got rid of those high frequencies. And why it got rid of that, it's exactly this frequency domain analysis that we talked about. Now, if you go to 50-day moving average, it's going to even get rid of more fluctuations. It's going to make your signal become more smooth, change less sharply. So this is your 50-day moving average. And if I really increase my moving average to 200-day, then it's going to become even less sharply changing. And it will now give you just a very general trend, but it's not going to capture any of the smaller changes that were happening in the signal. So one of the key reasons that you want to use a moving average filter is to get rid of these sharp fluctuations, get a sense of what the trend is really looking like. And to understand that, of course, you have to look at what is the frequency response of my filter. You understand the frequency response of the filter, and then you can understand the effects of that in the time domain better. So to reiterate, the moving average filter makes the sequence smoother as m increases. So that concludes our discussion of the frequency domain understanding of discrete time systems, which is very similar to the continuous time systems. We gave an example of the moving average filter to help us better understand what can the frequency domain analysis teach us. Now, we still have some missing pieces of information that we want to cover to get the main ideas of digital signal processing, to get the foundation of digital signal processing in place. So the first piece, or the first question we want to address is, how are continuous time signals transformed to discrete time signals? We understand continuous time signals, we understand discrete time signals, but what is the bridge between them? And the second question is, if you transform a continuous time signal to a discrete time signal, then how are the frequencies of continuous time signals mapped to the frequencies of discrete time signals? Because the units of the two frequencies are completely different. One is radians per second, the other is radians per sample. One goes from minus infinity to infinity, the other fundamentally is limited between minus pi and pi. So what's the relationship? And then the third main question we want to address is, how can discrete time systems be used to mimic continuous time systems? Because at the end of the day, what you really want is to do digital processing on continuous time signals. So someone will say, here is a speech signal, get rid of these frequencies in that speech signal. Now, all that description is in continuous time. How do you map that description to discrete time, and how do you then implement that continuous time operation in discrete time? These three questions are the thing that we'll be discussing in the next few lectures.